Well, this is a man who truly needs no introduction. Our longtime member and friend, Mark Dahmke, will do our speech tonight.
I decided to revisit my very first Torch Club paper, which was in March of 1987. And I think there are two members here, Bob and Scott, who were here at the time and might remember at least the title. But anyway, so a lot has changed since then, and so I thought I'd just kind of revisit this and expand on it a little bit, a lot actually. The first paper was came about because of an editorial in the Lincoln Star by Bill Dobler, advocating in favor of permanent daylight saving time. This brought a reply from a reader who preferred that we stay on God's time. That triggered a reply from me pointing out that even on standard time, the reader is not on God's time because time zones were established by man in the 1880s as a way of simplifying and coordinating railroad schedules, which I've since learned is not entirely accurate. Dobler replied, noting my comment about God's time being defined only by sunrise and sunset, but pointed out that the reader could have been right about God giving us time, but wrong about which time he gave us. Quote, "The story of creation just didn't go into that much detail," Dobler wrote, and went on to say that what he liked about God's time was that it seemed to be less demanding than man's. Quote, "His only measure of time was a lifetime, and we remain uncertain as to when that starts and mercifully in the dark as to when it might end." Back to the reader's letter, she complained that daylight saving time was confusing. I can't understand why man has to improve and change things he has no business messing with. Why can't people who like it so much just get up an hour earlier and those of us who don't like it get up with the standard time? And, quote, "I feel that God did a good job. Why do people have to mess it up?" But if she really wanted to be on God's time, she would have to use local apparent time. The easiest way to measure one solar day is to measure the position of the sun at local apparent noon or high noon on 2 consecutive days. But since the Earth's orbit is slightly elliptical, an apparent solar day can be 20 seconds shorter or 30 seconds longer than a mean solar day. Long or short days occur in succession, so that difference builds up until the mean time is ahead of apparent time by 14 minutes on February 6th, and behind apparent time by about 16 minutes near November 3rd. The equation of time is the difference. The real problem is that for most of history, the rotation of the Earth was our clock, but it only tells time in units of one solar day. When we needed greater precision, we had to find ways to break it down into hours and then minutes and seconds. When we had the ability to precisely measure seconds, we ran into a big problem. The Earth is not an accurate clock. The length of the day varies for a variety of reasons that I'll get into later. Much of this paper is about the workarounds that we use to live on a clock that doesn't keep time very well, and the workarounds we employ to live on a spinning globe. The rotation of the Earth defines the length of a day, but is there a more consistent or accurate way that we can determine the length of a day? The stars are so far away from us that their position appears to be constant for very long periods of time. What if we measure the day by observing the position of a bright star? The time it takes for a star to return to the exact position it held the previous night is called a sidereal day and is 1,436 minutes long as opposed to 1,440. This diagram shows the movement of the Earth around the Sun. Each day it moves about 1 degree in its orbit. The stars seen at midnight on successive nights will appear to shift westward as the Earth moves counterclockwise in its orbit. A star will arrive at the same location 3 minutes and 56 seconds earlier each night. We could just as easily measure the time it takes for the moon to return to the same position in the sky. This way of measuring time is extremely useful when it comes to predicting high and low tides. The lunar day is 1,490 minutes long because the moon drifts eastward against the stellar background 13 times faster than the sun does, completing an orbit in only 29 and 1/2 days. With respect to the stars, we have to wait an additional 54 minutes each night for the moon to pass overhead again. Lunar time isn't good for much other than keeping track of tides because it rapidly gets out of step with solar time. Originally, the length of the hour, minute, and second were defined as fractions of the tropical year, but in modern times, precise measurements have shown that the rate of rotation of the Earth and the length of the year change gradually for a variety of reasons. The tidal drag of the moon is slowing the rotation of the Earth, and changes in the Earth's magnetic field and in the liquid core of the planet cause it to speed up and slow down in unpredictable ways. To solve this problem, 1 second is now defined by the oscillations of the cesium-133 atom instead of being 1/86,400th of a solar day. This is known as atomic time. Because the length of a second is now decoupled from the rotation of the Earth, we occasionally have to add or drop leap seconds to keep atomic clocks in sync with the solar day. More about that later. Assuming that we use solar time as the basis for dividing the day into parts, we have to contend with the variations of the Earth's orbit, its axial tilt, and other factors. As I mentioned earlier, this is the equation of time. What is shown here represents the gain and loss in the Earth's elliptical orbit, and there are other factors that require small adjustments. This slide shows the position of the sun at noon standard time in the winter or daylight saving time in the summer. Because of the combined effects of the equation of time and daylight saving time, on July 1st, the sun is not directly south until 1:30 p.m. Central Daylight Time. The image on the right shows the position of the sun without regard to taking into account daylight saving time, and that's called the analemma, figure 8 shape. Prior to the Industrial Revolution, the system of local apparent time served us well, since the average time at which you could move from place to place was about 4 miles per hour. With the invention of the steam engine and railroads, it suddenly became possible to cover vast distances in a matter of hours, and more importantly, it could be done on a fairly reliable schedule. Suppose you board a train in Lincoln at 12:30 p.m. local apparent time. This is based on the position of the sun at local apparent noon in downtown Lincoln. You travel to Omaha at a speed of 25 miles per hour and arrive at 2:07 p.m. according to your pocket watch. The longitude of downtown Lincoln is 96 degrees 42 minutes west, and Union Station in Omaha is 47 minutes of longitude east of Lincoln. Each degree of longitude corresponds to 4 minutes of time. So, the time of local apparent noon in Omaha is 3 minutes and 8 seconds earlier than it was in Lincoln. When you arrive in Omaha, it will be 2:03:52 p.m. local time. If we consider a trip from Omaha to Des Moines, the difference increases to 9 minutes and 40 seconds, or enough to cause serious scheduling problems. Timekeeping on North American railroads in the 19th century was complex. Each railroad used its own standard time, usually based on the local time of its headquarters or most important terminus, and the railroad's train schedules were published using its own time. Some junctions served by several railroads had a clock for each railroad, and each one showing a different time. Because of this, a number of accidents occurred where trains from different companies using the same tracks mistimed their passings. Several attempts were made to standardize, but none were universally accepted by the railroads. Finally, the chief meteorologist of the U.S. Weather Bureau divided the U.S. into 4 zones for consistency among weather stations, and in 1883 convinced the railroads to adopt the same time zone system. Naturally, there were those who did not appreciate the change. On November 23, 1883, the Sydney Journal reported, quote, "We will turn the clock back just 28 minutes, and what will become of the 28 minutes? They will be lost, dropped out of existence as though they had never been. We will be 28 minutes younger than we were." The Cleveland Evening Post states, quote, "Radical changes, no matter how reformatory, which break up old customs, almost sacred because of their antiquity, are never submitted to without grumbling." Not long after the introduction of standard time, long-distance telephone service became available between New York and Chicago, extending to Denver by 1911, Later still, radio and television programs and news broadcasts had to be recorded and time shifted to accommodate East and West Coast primetime reception. Daylight saving time was first enacted in the U.S. in 1918 in the interest of adding more daylight hours to conserve energy, and was implemented again in World War II. It was never popular with farmers who actively lobbied against it due to its impact on farming. Every few years, another bill is introduced to switch us to permanent daylight saving time or permanent standard time, but in my view, this doesn't really address the larger issue. Also, technology has changed dramatically in the last 40 years, as has our need for much more precise timekeeping and coordination. Most, but not all, astronomers, both amateur and professional, prefer that we go back to standard time, myself included. Time shifting in the jet age becomes complex when you fly across the international dateline, sometimes arriving before you left, based, of course, on the clock you're looking at. Ever since there have been time zones, there have been people complaining about living near a boundary line, especially if your city happens to be on the boundary. This is one of my favorite XKCD cartoons. It's the edge cases that cause most of the angst. In this case, Emily was born exactly at the North Pole in every time zone at once on February 29th, and the airline was in the process of changing ownership between countries. Okay. For convenience and political reasons, time zone boundaries have taken some unusual twists and turns over the past century. I would even go to say so far as to say that time zones are now as politically charged as language and cultural identity. In my 1987 paper, I offered a possible solution. Arthur C. Clarke once suggested that we could switch to 4 6-hour continental time zones. However, looking at the current map and noting where some of the lines are drawn, it's probably best just to do away with the whole idea of trying to have nice orderly 1-hour zones and let each country do its own thing. China is geographically wide enough to span 5 time zones, but the entire country follows Beijing time or Zone 8. Malaysia is spread across 2 time zones, but the country uses Zone 8. Cambodia, Thailand, and Vietnam are directly between China and Malaysia, but chose Zone 7. The international dateline and associated time zones are a confusing mess. Samoa and American Samoa are just 50 miles apart, but are a full day apart because of the international dateline. The nautical dateline, which is not the same as the international dateline, is a de jure construction determined by international agreement. It was the result of the 1917 Anglo-French Conference on Timekeeping at Sea, which recommended that all ships, both military and civilian, adopt hourly standard time zones on the high seas. The United States adopted its recommendation for U.S. military and merchant marine ships in 1920. This dateline is implied but not explicitly drawn on time zone maps. It follows the 180-degree meridian, except where it's interrupted by territorial waters adjacent to land. In theory, ships are supposed to adopt the standard time of a country if they are within its territorial waters, then revert to international time zones as soon as they leave. In practice, the ships use these time zones only for radio communication and official purposes. For shipboard purposes, such as work and meal hours, they use the time zone of their own choosing. Since the initial concept of nice orderly 15-degree longitudinal zones has been thrown out the window due to geographic and political boundaries, and since we now use GPS and computers to navigate and tell time, I think a more feasible option would be to adopt my time, quote unquote, or circadian time, which means that we would all have multiple clocks, one synced to your circadian rhythm, another for official local time and universal time. Your clocks and internet-connected devices can keep track of the time zones for you. In the internet era, the world effectively runs on universal time. The actual standard is called Coordinated Universal Time, or UTC, and is within 1 second of mean solar time at 0 degrees longitude, which, in other words, is Greenwich Mean Time. If you work the night shift, you could set your watch to noon, so that your noon is 2 a.m. standard time. Or if you're an airline pilot, your watch could display your circadian time and universal time, which is the time used for everything aviation related. Modern smartwatches can monitor your pulse and blood pressure, so why not let the smartwatch monitor your vitals and determine your optimal circadian time? It can also easily convert back and forth to local time and can assist with scheduling appointments with others who are operating on their own time. Timekeeping in computers is done by incrementing a counter every millisecond or thousandth of a second, in some cases every millionth of a second. In most computers, the current time is represented as the number of non-leap seconds since January 1st, 1970. This is known as epoch time or Unix time, since most computers and the majority of timekeeping servers run a variant of the Unix operating system. Unix time differs from Coordinated Universal Time and International Atomic Time, as if we needed another one, in its handling of leap seconds. While UTC includes leap seconds to adjust for discrepancies between atomic and solar time, Unix time does not. When your computer, phone, or smartwatch displays the time, it's retrieving the UTC universal time value in seconds since 1970, converts it to local time, and then takes into account your time zone and adds any leap seconds, and that's what's displayed on your phone. It also knows when to apply daylight saving time based on your location. Another favorite cartoon. There is a critical software component that we all depend on that is used in virtually all computers, internet-connected appliances, and millions of other devices. It's called the Network Time Protocol. There's a module that runs as either a client or a server in all of these devices and many other places you would not expect. By the way, NTP is well maintained by the Network Time Foundation, not some random person in Nebraska. Thankfully, not me. An oversimplified description of NTP is that it's designed to mitigate the effects of delays over networks such as the internet, where the transit time of data varies with distance. In the old days, keeping clocks to within a few seconds was good enough, but now world markets depend on much greater accuracy. Almost every computer has a real-time clock, but all clocks drift slightly and get out of sync. NTP provides a way for all the billions of clocks in the world to stay in sync with each other. NTP was designed in the early 1980s and can achieve better than 1 millisecond accuracy under ideal conditions. On a global scale, NTP can maintain accuracy in the range of tens of thousandths of a second. The Precision Time Protocol, or PTP, was created in 2002 to solve a problem. The older NTP was no longer accurate enough. PTP enables sub-microsecond accuracy or even billionth of a second accuracy, which is suitable for measurement and control systems, financial transactions, and networks that require precise timing. Today it's used in places where even the tiniest difference in timing can have a huge impact, such as mobile networks and stock trading systems. Both NTP and PTP had the ability to compensate for speed of light delays and transmission latency across global network internet connections. This board, pictured here, will give you billionth of a second accuracy for a mere $9,000, which is cheap compared to the old systems. Actually, there are cheaper options. One is only $200 with slightly lower accuracy. It would be fun to buy one of these to play with, but I can't think of a good personal use case for it. Fiber optic cables are preferred over satellite links, which have a significant speed of light delay, but even fiber optic connections have speed of light delays and other latency issues that make timekeeping difficult, even over short distances. However, a signal transmitted out to geostationary satellite, 23,000 miles and back, relayed to a ground station on another continent, has an even worse minimum delay of about 270 milliseconds, or almost a quarter of a second. We now have in place the infrastructure to manage timekeeping on a global scale and take into account the delays associated with speed of light and network latency. How do we extend these services to other planets? NASA has been directed to establish a lunar time zone to aid in coordinating international missions to the moon and future lunar bases. This is more complicated than it sounds because, due to the theory of relativity, time passes at a different rate on the surface of the moon than on other planets. While the difference is small, it cannot be ignored. You might have heard that time slows down near a black hole due to its extremely strong gravitational field. An observer far away from the black hole will see events near the black hole happening at a slower rate than an observer near the black hole. This holds true for any gravitational field, not just black holes. A mountain climber with an extremely accurate clock would notice that time is passing slightly faster at the top of Mount Everest than at sea level. The takeaway for this slide is that time is passing at a different rate for every marked location on this chart. This would have been an astonishing concept to anyone living before Einstein published his theory of special relativity. This chart shows cislunar space, the area including the Earth and Moon system near the nearby Lagrange points. The Lagrange points are locations where the gravitational influence between the Earth and the Moon are at equilibrium. Using L1 between Earth and Moon as a reference, if you move closer to either the Earth or the Moon, time passes more slowly. Since gravity at the surface of the Moon is lower than the surface of the Earth, time passes at a slightly faster rate, on the order of 58 microseconds per day. This sounds like a small number that can be ignored, but it accumulates. Over 50 years, since the Apollo landings, the difference is 1 second. Any atomic clock placed there will gain time relative to an Earth-bound clock. The same holds true for Mars, but clocks on Mars will diverge at a different rate because gravity there is stronger than on the Moon, but not as strong as on Earth. If it's just the Earth and Moon, we could probably ignore it and the problem by introducing leap seconds and keep the clocks in sync, but still this doesn't solve the real problem. Humans could compensate for it, but computers operating at speeds of where a millionth of a second is a long time must take into account. Now that we've established the need for taking into account time dilation, we have neglected the other side of the original time zone problem. On the Moon, it's pretty easy to solve because a lunar day is the same as the period of rotation around the Earth. There's no need to divide up the Moon into separate 1-hour time zones because no one who would live on the Moon would tell time that way. The sensible thing to do is to pick a time zone that synchronizes with Earth-based ground control, or UTC, universal time. The Apollo missions operated on Central Time because the control center was in Houston. The lunar time servers will still have to keep track of the time dilation effects. Mars presents a different set of problems. A solar day on Mars, also called a sol to distinguish it from an Earth day, is 39 minutes longer. For the Mars exploration rovers and other missions, the operations team at JPL worked on Mars time, with the work schedule synchronized to local time at the landing site on Mars. My friend Negin Cox lived on Mars time for months as part of the operations team on 4 Mars rover missions. She and her team wore wristwatches calibrated in Martian time. This resulted in the crew's work schedule sliding approximately 40 minutes later each day. The beauty and longevity of our current system of timekeeping is that it's based on the numbers 12 and 60. 60 is the smallest number divisible by the first 6 counting numbers and by 10, 12, 15, 20, and 30. 24 is divisible by 3, 6, and 12. This was all perfected by the Babylonians, who borrowed it from the Sumerians, who invented it in the 3rd millennium BC. If future residents of Mars decide to keep the 24-day, 60-minute hour, then the length of 1 second would have to change. One possibility is decimal time. They could switch to decimal time. China used decimal time alongside duodecimal time through most of its history. It was used until 1645, when a new calendar based on European astronomy was brought to China by the Jesuits. France attempted to switch to decimal time several times, but it never caught on. The 24-hour day has become so ingrained in our culture that, like the author of the letter to the newspaper, it seemed like it was created by God and it's unlikely to ever be changed, at least on Earth. Mars residents might decide to switch to decimal time to just make a break from the home planet, and it might be easier to change the nomenclature to avoid confusing Earth time with Mars time. In 1998, the Swiss watch company Swatch introduced a line of digital watches that divided the day into 1,000 beats, each being 86.4 seconds long. 1 centibeat is 0.864 Earth seconds. A centibeat on Mars would be 0.887 seconds, which would be close enough to 1 Earth second so that mentally converting between seconds and centibeats wouldn't be much harder than remembering that 1 yard is about equivalent to 1 meter. Mars will also need its own time zones and its own atomic clocks, but the planet will always be out of sync with Earth because of the length of its day and its surface gravity time dilation, and will always be anywhere from 5 to 21 minutes out of sync because of the speed of light communications delay. So, does anybody really know what time it is? Before railroads, computers, and space travel, timekeeping was relatively simple, but eventually time zones had to be added to accommodate our need for speed. Theory of relativity was the final nail in the coffin for a deterministic clockwork universe, when Einstein showed us that there is no standard clock for the universe. Different observers disagree on which events happened at the same time. Although time's arrow seems like a fundamental property of our universe, it's likely that it's just an emergent property. Our awareness of the passage of time is related to our perception of our environment. The Earth spins on its axis, so we count the days and years. We experience a one-way flow of time because we and the world we perceive are made up of countless chemical and physical processes, which are inherently irreversible. So the time we're measuring is not a fundamental property of the universe, but merely an illusion, a measure of change. We create clocks and time zones so that everyone's illusion of time stays aligned so that our society can function. Thank you.